Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm pleased to introduce Nico Hansen. He's a visiting researcher in constant reasoning for 3 months. So I guess for another 2 months, something like that. And he's working with us on a general genetic optimization package that we are building, which is targeting simulation and optimization scenario, specifically for Azure, the Azure customer. Internal customer is Azure. And Nico is a researcher at INRIA in Paris. Although he's German, but he works for a French institute. And is a specialist of optimization with genetic algorithm, continuous optimization. So he's going to give a talk which describes, I guess, his biggest contribution to the field, which is the CMA-ES algorithm.
Okay, so I will give a short introduction to the problem. It's about continuous black box optimization. I will give a mathematical formulation. I will give some applications of black box optimization in general. And I try to ask the question or answer the question, why actually is this problem difficult? And then I will present a stochastic second order black box optimization method, which I believe is pretty much developed or constructed from first principles. It's called CMA-ES. I would like to talk a bit about design principles, in particular about invariance and others, and if I have time I will present experiments results. Again, feel free to ask questions and to interrupt me. Okay, so this is the problem we try to tackle. We have a function f, which is called objective function, cost, loss, error, or fitness function, which we want to minimize. It's a given function, and we want to find a solution x which minimizes, which gives a low cost value or low fitness value. Okay, I will talk about fitness even though we want to have a low value. It's a continuous function that it's a function from in the continuous domain. It maps r to the n to r, and we consider this function completely as a black box. That means we don't know properties about the functions. What we can do is we can take points in the r to the n. We can put the points into the black box, and we get a function value out, and that's the information on the function we can get. In particular, that means that we assume we don't have cheap gradients, because gradients are usually extremely useful to do optimization in continuous domain. So we don't have cheaply gradients available, or they might not be useful, which can also be the case. And the problem-specific knowledge we have, we put into the black box. Of course, if we have a real problem, it makes a lot of sense to formulate the problem in a way that it's comparatively easy to solve. So we put everything we know about the problem into the black box, and then we tackle this black box problem. Typical problem dimensions are between 2 and 200, and the objective is to find a solution x in the r to the n with a small value of f of x. The search costs we define as the number of calls to the black box. And well, that's about the mathematical formulation of the problem. You cannot get lost on this slide, so you have to ask questions here. Okay, so these are typical applications of this kind of problem. Model and system calibration. So if you have a biological, physical, or chemical model, usually in the model you have some constants and some parameters, and you have data, and the model produces data, and depending on the constant, you will fit the constants such that what the model output fits the data in the most appropriate way, the real data. It's a very common problem, and the model often will be simulated on the computer. You might have a production process, which is again simulated on a computer, which depends on parameters. Also a typical black box optimization problem, well, not necessarily black box, but still. Another typical problem is optimization of control parameters, like the movement of the robot, like a trajectory of a rocket, like the stability of the gas flames. These are 2 applications I've done personally. This was actually an experiment in the laboratory. So it's not necessarily that the black box is a computer simulation. It can even be an experiment in the laboratory, which takes a minute or half an hour or something. Another very typical optimization problem is shape optimization, like curve fitting, or if you want to find a design for some aerodynamic or fluid dynamic body, like an airfoil, like a spoiler, like a wing, or like an airship. Again, there's a simulation involved. We do a fluid dynamic simulations and get as output the fitness of the shape or the quality of the shape. So two more specific examples. This actually doesn't really fall in one of these three categories, but it's a nice example because it's also a nice comparison between different algorithms. What you see here is a CT image of a human body. Here you see the vertebra. Here you see the spinal cord. Here you see the spine of the upper vertebra. So this is the CT image. This is an ultrasound image. And if you don't see much, it's exactly what you're supposed to see. You don't really see much on this image. So this is an image you can not do during an operation, but this image you get during the operation. And the problem is now to project the surface of the bone, which is annotated here, into the ultrasound image. So that can be formulated as an optimization problem. You would like to have this interoperatively. And well, if you do experiments on this, these are results on about the image registration of 12 vertebrae with 1,000 different starting positions. What you see on the x-axis is the misalignment, the final misalignment of the pictures. On the y-axis, you see the fraction of trials. That means you see a CDF, an empirical cumulative distribution function. Well, you see the median error of CMA was about, well, a bit larger than 0.001 millimeter, maybe 0.002 millimeter. You also see that almost all images were aligned with an error less than 0.1 millimeter. With CMA, there are three other methods. These are classical methods, Quasi-Newton methods, BFGS, conjugate gradient method. This is the air-prop method, backpropagation method, improved backpropagation. And you see that clearly the best results come from this method, and the other methods align clearly worse. Of course, one question, yes?
So is that because those are local methods?
Yes, that was exactly the last sentence. Of course, one important question is why is this actually the case? And well, we don't know exactly, but we have some idea why that is the case. One nice feature of this study is actually that this was done in a restart procedure. So it's maybe, yes, here it's said in the multi-start procedure. That means, yes, these are local methods, but if you apply them in a multi-start procedure, they often perform also in a more global setting. Yes.
In order to plot misalignment, you need to know the actual position, right? How do you know it?
Yes. It's not my work, so I'm just looking at it. I don't know how they did it, but I assume they knew it, yes.
I was about the same thing, like the image resolutions are usually more than a millimeter pixel.
Okay, so...
To get that resolution is, yeah, but if it's not your paper then.
Okay, yes, so this one, I don't know. Okay.
But would this be a case where gradient would be available but not that useful?
No, I don't think so that gradients are available.
Or it wouldn't even be available, you think?
I think it's in the black box scenario, but even if they would, I think you're right, even if they would be available, they would not be very useful, because you can assume that the landscape is rugged. Yes. So you have probably many kind of local optima, but more or less a global shape. I assume that is actually the case. Okay, I will come to this in a minute. So this is a second example. Mainly I choose it again because you see different methods, and also because it's one movie in this talk you will see. So it compares 4 different methods for a tree pad which has to walk in this direction, and the objective is simply to walk fast. And you see overall 4 methods. This is just pure random search. It's always a good idea in a benchmark, at least in an artificial scenario, to check what pure random search can do. This is f-mean search, which is a function in MATLAB, the well-known Nelder-Mead method. Then we have IDEA, which is an evolutionary computation method. And we have CMA, and these are the movements of the four methods. So clearly see the problem is non-trivial. So if you do a random search, well, you do a very little bit of movement, but not much. You see that f-mean search is not as good as IDEA and CMA. I think the reason here is probably that f-mean search doesn't tackle problems with a larger dimension world. This is about a 20-dimensional problem, and f-mean search is a very good method for, let's say, 5 or smaller dimension, but not for 20 dimension anymore. IDEA is actually an algorithm which is quite similar to CMA, but still it doesn't perform as well here. And I would say it's hard to say whether this solution is not really optimal. The movement looks pretty optimal. Clearly, you see that these algorithms didn't find an optimal solution. For CMA, I wouldn't be sure, actually.
It seems difficult to improve the movement.
Yes, that looks like that.
So these are the final solutions. So the policy, so to speak, for controlling here is what's being optimized, and this is now running these robots.
Exactly. So yes, I didn't say that, but yes, that's the final solution. So you don't see any evolution or so. In both cases, you just saw final solutions.
Excuse me, how the behavior is encoded here? So is it based on like some feedback from the actual from the sensors, or is it like a fixed pattern of movement?
No, you have a fixed pattern for the movement. Yes.
Ah, okay. So.
You sure it's the right movement?
So what let you think it's not the right one?
It's not the right one.
So this is another example I just got to know 2 months ago. It's from the RoboCup in the simulated soccer league, where a 3D simulation of the nano robot is done. This is the nano robot. It's a real robot, and the league is a simulated one, and the University of Texas at Austin won this competition amongst 22 teams. More surprising is they won all 24 games, and they scored 136 goals and conceded none, which means they were pretty good compared to all the others. And the reason is they optimized their agent. That's, I think, the main reason. They were the ones that really did optimization on the agents. They used CMA, but I think the main point is, of course, to do the optimization. And this led, actually, so compared to manual setting of control parameters, it's simply a better thing to do, but they did a lot of number crunching to do this.
What did they optimize for?
They optimized actually for many different things. So I won't go into detail. I think one very important thing they optimized for is to run fast. As simple as that. So to have a ball in front and just to run fast with the ball in front of you. And if you can do this, well, like in real soccer, it's already something.
So no one's tried optimization before then?
Well, I think in this competition, so for other competitions where they had different agents, they did this. Yeah. But I think they thought it's not possible here because it's too difficult, or I don't know. So I guess that's the reason. But maybe also one reason is that many methods don't really work. So maybe it's a difficult problem. And also you have to separate your optimization goals, right? So if you take the optimization goal to win the game, that's a bit hard. So you have to really find specific optimization goals like running fast with the ball, and then I think it works pretty well. Okay, so back to the question why. So why actually does it work? Or why do certain methods work better than others? So to answer this question in a more abstract way, we ask the question, why is it actually difficult to do black box optimization? And I think this is almost a pretty complete list of difficulties. So if you have these in mind, in 90% of the cases, or even 95% of the cases, you know already what's going on or why it doesn't work. Okay, we assume, of course, that we have a nonlinear and non-quadratic function. Otherwise, okay, a quadratic function, we would do different things, and it might also be non-convex. So this would be a non-convex function. It's still completely smooth, well, besides on this one point, but it could anyway be smooth also there. Then dimensionality is really an important aspect. So if you have a one-dimensional, two-dimensional, three-dimensional function, it's usually much, much easier to solve than a 10-dimensional function. The reason is simply that the search space volume increases exponentially. Okay, and if the function is separable, you just can optimize subspaces, and that's an easy task to do, at least if you know the subspaces, if you know so functions are hard if they are non-separable. That means if we have dependencies between the object variables and if they have dimensionality, let's say, of larger than 5. That already makes the problem not so easy to solve. Ill conditioning is a really important problem. On a pure quadratic function, this is well defined as the condition number of the Hessian matrix. Well, the problem remains the same on non-quadratic problems. The problem is that certain directions in search space have a very, very different sensitivity. And a different way to say that we have valleys which are very long and very narrow. And that's very difficult to deal with, to follow these kind of valleys. So that's not really an ill-conditioned problem, but here already you see if you are here on this function, in a 2D function, if these are lines of equal fitness, the gradient direction goes in this direction and the Newton direction goes in this direction. You see that the gradient direction is not really useful. So if you only do gradient steps and if the condition number is much larger, it takes very, very, very long to get close to the optimum. That's a real big problem in continuous optimization. And ruggedness, of course, it might not be fair because I have subsummed here many different things under ruggedness, non-smoothness, discontinuous functions, multimodal functions, noisy functions. So you could go into detail here, but I think really one of the main features is that with evolution strategies we can solve this function in a smooth way. So this is a section through a 5D landscape. And while looking at the section, you basically have complete information, right? So you see, everywhere you see the function value, which means you would point to this point to be the optimum. But of course, if you do here like 3 function elevations and try to find a gradient in 5D, well, that's a pretty difficult thing. Actually, it will not work at all. The surprising thing is really, okay, I designed this function particular like this. This can extremely smoothly optimize. So in the optimization process with an evolution strategy, you will hardly recognize that this function is rugged at all, that it's difficult. And that actually surprised me as well. Okay, it's specifically designed for that. But I think that's one of the reasons why these methods work, because they can cope with this kind of landscapes. Okay, so talking about black box optimization, I give a short overview of methods which are available. Typical gradient-based methods still for black box. We can estimate the gradients numerically, like conjugate gradient method, Quasi-Netwon method, which are second-order methods. There's a whole bunch of derivative-free optimization methods, like trust region methods, NUOA, simplex downhill, you have seen it already, as F-mean search from MATLAB, pattern search methods, and we have stochastic methods, evolutionary algorithms. I will talk a bit about evolutionary algorithms, simulate annealing, for example, SPSA, for example. In the domain of evolutionary computation, we have typically 3 main branches, also historically: genetic algorithms, evolution strategies, and genetic programming. And the best way to differentiate between them is to look at the search domain. They are operating on genetic algorithms, operate on bit strings, evolution strategies operate in the continuous search space, and genetic programming operates on trees. So I will talk about evolution strategies. I won't talk about much the biological motivation. This will be one slide where we see, well, evolution is an optimization process, and we can make the comparison in evolutionary computation. We talk about individuals, offspring, parent. In optimization, we talk about a candidate solution or a vector of decision variables, design or object variables. We have a population, which is an important concept, I think, actually, in evolutionary computation, which is a set of candidate solutions. So we usually operate on a set and not on single candidate solutions. We have a fitness function, which is an object loss cost or error function, and the generation and compared to an iteration. Okay, so this basically concludes the general part of the talk. Now I'm going to specifically design a method. Well, you could just call it a stochastic optimization method. Well, the template is basically useful for any kind of optimization method, I would say. So what we have here is a probability distribution which depends on some parameters theta. So we have to initialize these parameters theta. We have to set a population size, and then while we are not happy, we do three things. The first thing is we construct or sample new solutions from the probability distribution. Solutions x in the R to the n, lambda new solutions. Second, we evaluate these solutions on the objective function. We get lambda objective function values. And third, we update the parameters of the probability distribution. And the update function depends on the old parameters, depends on the solutions we have sampled, and depends on the function values, well, in some sort of weird way. And, well, when we are happy, we might return the expected value of the distribution, we might return the best solution we have seen, whatever we want. That's an extremely generic template, right? You can think of the probability distribution as a method to construct new solutions or a method to construct good solutions. And then this template is just a generic template for black box optimization, for black box optimization method. One thing which is maybe funny to realize here is that before our problem was to search x values in the R to the n. Now we sort of switched this problem. We are searching for a good theta vector, so for a good method which produces good solutions. So we are searching basically in the theta vector space, in the probability distribution space, and not in the Rn space anymore in some way. Well, there are basically three questions which are open here. What is the P, so which kind of probability distribution you are using for sampling? This objective here, which turns out to be, well, in some way trivial, at least from a practical viewpoint, and how to update the parameters. Of course, this is the most important part. Any questions?
The role of the W, I don't quite, are you going to elaborate on that?
A little bit, yes. Actually, it removes some information. I think it's actually quite an interesting thing. But yes, I will talk a bit. Okay, so this is the instantiation again. So actually this template, if we would remove here R to the n with search space, it doesn't depend actually on the domain, right? We can sample in any domain, and we can do all this, and actually we find policies how to do it specifically, more or less independent of the domain. Anyway, we go to the continuous domain, we ask what kind of probability distribution we are choosing, and the choice is to the maximum entropy distribution. In continuous domain, this is the multivariate normal distribution, so that's our probability distribution we are choosing. Regarding the W hat, what we do is we just take the ranking of solutions. So we have here lambda solutions, and the only information we actually put into the update function is the ranking of the solutions. This determines the W hat more or less up to some shaping function, which is an internal parameter of the algorithm. That's actually a nice feature, and I will come to it later, why it's actually a nice feature. We apply natural gradient descent on the distribution parameters. That means basically we maximize the improvement of the expected fitness. So we change the parameters that we maximize the improvement of the expected fitness. It's not at all trivial to see how to do this. And we use some additional non-local information, basically low-pass filtering and striving for conjugate orthogonal steps. These are very well-known tricks in continuous domain as additional feature in the algorithm. So the algorithm is CMA-ES, covariance matrix, adaptation, evolution strategy. I will talk about the normal distribution on maybe 1 or 2 slides. Most of you probably know this. That's a 1D standard normal distribution. The density, that's the density of a 2D standard normal distribution. These are lines of equal density. In general, the lines of equal density are ellipsoids, yes?
Just a couple of questions. So one is, how do you pick the covariance matrix for the normal distribution?
Yes.
And second being that you get this rationale that you're taking the normal distribution because it is entropy maximizing.
Yes.
But any kind of entropy maximizing function only depends on the probability distribution. It does not depend on the value that the function picks. While your optimization objective might be sensitive to the specific values, not just the distribution.
Well, we actually don't use you mean the values of the objective function?
I'm saying that the reason you gave, I mean, you said that you're picking normal distribution because it's entropy maximizing.
Yes.
But entropy does not depend on the specific values. It only depends on probability distribution.
No, it's the family that
Yes.
you choose, the family of multivariate Gaussians.
Yeah, that's right.
And it's the maximum entropy solution given the constraint of the first and second order moments.
Yes.
But it's family choice. And then he has the parameters. Sorry, I'm interpreting, but and now he's optimizing the parameters within that family. That's how he.
I was also a bit short because there are other reasons. It's in particular also a very practical distribution to deal with. So that's another reason to actually choose it. Yes, the question was exactly right. So how do we choose the covariance? So this would be again a normal distribution with identity covariance matrix. These are 200 samples. If we change the covariance matrix to be non-identity, then we might end up with this ellipsoid as equal lines of density. These would be 200 points sampled from this distribution. So in general, we have a multivariate normal distribution with a full parametrization, complete covariance matrix, and the mean vector, which can be noted like this, the normal distribution with a mean and the covariance matrix. So the point would be sampled in BR to the n. Our parameter vector theta is the mean and the covariance matrix, while the mean can be interpreted as the prototype solution, and the covariance matrix determines the variation around the mean. That means writing a point which is normally distributed, or a point which has point m plus a normal distribution with zero mean is actually the same thing. So therefore, covariance, therefore the name variance, because it talks about variation. Okay, one thing also to notice here is that if you look at the density basically depends on the distance to the mean, and the distance is taken in a way depending on the covariance matrix. So if the covariance matrix is the identity, it's a Euclidean distance. If it's non-identity, it's a Mahalanobis distance. So the points on this ellipsoid would have all the same distance to the mean if we interpret this as a distance measure. Okay, so now we are ready to answer the question, how do we actually change the parameters? So what kind of covariance matrix we choose, so what kind of mean value we choose. So let's say I will give just one iteration of the algorithm, which samples in the beginning, let's say 7 points. This is the mean of the distribution. We start with the identity as covariance matrix. We sample 7 points in 2D. We rank the points and select the 3 best ones, let's say, and then we take some average of these best points, which would be this vector, the vector between the original mean and the average of the best points, yw, and this is how we move the mean. And the new covariance matrix is computed by a mixture of this line distribution and this original distribution. So we elongate the covariance matrix in the direction of the movement, and we reduce the variance in all other directions. If we write this, it's simply a discount factor in front of the old covariance matrix, and 1 minus the discount factor times the outer product of this vector, which gives the new covariance matrix. And this is the new distribution. And this is basically the complete update, yes?
So W does not just depend on a single point, but really depends on the ensemble of points. Otherwise, you wouldn't be able to formulate the ranking as a point-wise operation. Yeah, it's just notation. I mean, you're just saying W of a single Y. But if you want to throw everything away after rank K, then that's not just a function of...
Yes, if you want to implement it, it's not a function of just F, but you can formulate it as a function of just F if you know the CDF of F. Knowing you can sample points in X, then you get a cumulative distribution function of F. Right? You look at the F of X values if you sample X.
Mm-hmm.
And if you know this CDF, then the W is simply a point in this CDF. But of course you don't have the CDF, so the nice way around it, the really easy way to round it, to get an estimate is just to rank the solutions and to, according to the ranks. Mm-hmm. This is actually something we don't know for such a long time, so that you really can formalize it like that.
So this W, is this just an ad hoc choice, or is there some intuition behind why you do this ranking?
Okay, I will come back to it later. I think it's really a cool property in terms of invariance of the algorithm, that you just use the rankings. One other algorithm which actually does it is the Nelder-Mead algorithm. It's a very successful one, and I think, again, one of the reasons why it's successful is actually that this is a property. I will come back with an example to this later. Okay, that's actually the complete update. Well, okay, there are small things which are added later on, but that's the complete update of the mean and the covariance matrix. You can repeat this, of course. Again, 7 points sampled, select the 3 best ones, take, let's say, some weighted mean of them. We have the movement of the mean. Again, we compute the new covariance. Now the result is actually much less predictable. Before it was very much predictable that this covariance matrix is just elongated in this direction. So now we sort of have some rotations going on, so it's not so clear anymore how it looks geometrically. And that's the final distribution after 2 steps. One thing to recognize is that a ruling principle in some way is just to increase likelihood of good points. So the update of the mean basically maximizes the likelihood of successful points. So this mean value is exactly maximizing the likelihood of these points, because the mean is where we sample with the highest probability. And the update of the covariance matrix actually increases the likelihood of these steps we produced. So by changing the covariance matrix like this, we increase the likelihood to produce these steps again, sampled from this mean and then with a new covariance matrix. So that's a ruling principle. Well, another one, as I said, if we look at the function or the expected value of W of F, actually we do a natural gradient descent in M and C like this, which is sort of a non-trivial result. Okay, these are very simple update equations, but they have quite some interpretations or impact in some way. So obviously we learn all pairwise dependencies in the variables. Because we just update the covariance matrix, we get non-zero entries everywhere, potentially. We do a natural gradient descent on theta to say something about natural gradients. The point in natural gradients is that they are independent of the parametrization of the distribution. And in this sense, they are unique. Basically, they comply with entropy, also with relative entropy, so that they under a minimal relative entropy change, they maximize the improvement in the fitness. Okay, that would be sort of the formalism to this. Another way to look at it is we conduct a principal component analysis of the steps. So we have here taken 3 steps, this one and this one. If we do a principal component analysis, and with these steps, then we end up with something like this, which leads us to a new coordinate system actually. So the eigenvectors of the covariance matrix are the principal components where the sampling is independent, and this is a new coordinate system. So we sample in a new coordinate system independently, which is adaptively learned by a PCA, and just like that we can view it as an adaptive representation or an adaptive encoding of the search space. The principal components define a new coordinate system. This is entirely independent of the coordinate system, the whole procedure. So that's, I think, also an interesting point to notice. And invariance is indeed a major design principle. And another point to notice is that this pretty much resembles a Quasi-Netwon method, which are variable metric methods in X space. So also here we learn a variable metric in X space, and it turns out that indeed the covariance matrix is adapts very close to the inverse Hessian matrix of a function f if the function f is convex-quadratic.
Just on that, so so what's the link between this and the kind of version of Kalman filtering where you're updating the covariance matrix as well?
I guess the link is pretty close.
Yeah.
You can also, I've put here some references. Well, this update is actually something which is, well, yes, done in different domains, also in control.
Yeah.
So I guess it's sort of independently invented in many domains several times.
So the covariance matrix that you draw here in the picture, its size more or less stays the same. But if you would actually run this algorithm further, you would expect it to shrink, right? If that's the number of iterations.
Not necessarily shrink, but you would expect that the distance between the original covariance matrix and the new covariance matrix becomes larger. But that depends, of course, on the underlying objective function. But yes, your point is correct, that depending on the learning rate, which is basically this 0.2, the changes cannot be big, and that's because you don't put enough information to make big changes. But over time, you can make arbitrary big changes.
But what I mean is, if the center of your distribution is indeed the minimum, the solution,
yes,
and you will run this algorithm further, then you would expect the covariance matrix to shrink
yes.
around this point, right?
Yes, that's a very good remark, and leads me to my next slide, because there's there's another. Okay, so it's related to that we actually choose this kind of sampling, which is the mean plus a scaling factor times normal distribution with zero mean and covariance matrix. So we have an additional scaling factor, and we have an adaptation for the scaling factor as well. But you're totally right. This is what's happening. Yes?
The fact that 0.8 and 0.2
Yes.
coefficients add up to 1, does it really matter?
Yes.
So are you using it somewhere else? Why should I don't see why it should add up to 1.
Otherwise, the update would be biased. So you would either, just by doing the update, you would either decrease the overall variance or increase the overall variance. And both, I would argue, is not really desirable. So that's actually one design criterion in the end of the algorithm, to have an update which is unbiased under random functions.
What do you mean increase or decrease?
Well, you can, if this y is distributed according to the covariance matrix, which would be the case if selection doesn't change the distribution, which would be the optimal case, because this means the distribution is samples in some way optimal, right? That even selection doesn't change it. So then the expected value of this term, so you take the covariance matrix, you take this term sampled from this, the expected value of this term would be again C. And this is only the case if you take the summons being to 1 overall. So it's simply an unbiased thing. And this you also see immediately in practice. If you run simulation, if it's biased and you have a little bit of noise in the function or anything, you really see immediately that it doesn't work. So yes, it's important. Okay, so we have a scaling factor here. And indeed, the covariance matrix shrinks, but indeed the covariance matrix often doesn't shrink fast enough because the learning rate is quite slow, because we have many parameters in the covariance matrix. We have a different, that's one reason why we have a different mechanism for step size adaptation. Another reason is that it actually adapts better step sizes. And so this is the idea for the additional step size control in the algorithm. We look at what we call an evolution path or search path. So we are in 2D again. Well, let's look at this picture. We start here, and then let's say the updates of the mean look like this. And then we look just at the sum here of six steps as an example. And if the steps all go into the same direction, the sum will obviously be long. So that's a good indication that we actually should increase the step size. Because if we just would have one step, this one longer, we would have ended up here and would have saved these 2 steps. So we look at the path. That's actually something which is done also different in other algorithms in some slightly different ways. I think it's a very useful heuristic to have in mind if you want to design algorithms in continuous domain. You look at the path of a few steps, and then here we just analyze whether it's long. If it's long, we increase the step size. This is a situation where it's short, so we do these 6 steps. Basically, the steps cancel each other out. They go back and forth, and that's exactly the situation where we should converge, because we can assume that the actual mean of the distribution is already close to the optimum, so we decrease the step size. Here we have a neutral situation. One cool thing is, because we know the distribution we are sampling, we actually can compute the neutral situation exactly. So we know the expected length of this path, and so we can exactly know when selection actually makes the path shorter and when selection makes the path longer, and we can implement this in the algorithm. Okay, so summing up the algorithm, we sample the normal distribution, which happens to be the maximum entropy distribution, which means we have the mean and we add something which has 0 mean with the covariance matrix and a scaling factor. We rank sampled solutions according to their fitness, which has an invariance preserving, which has an invariance property. I will talk about that in 5 minutes. We update mean and covariance matrix by increasing the likelihood of good points and good steps, which means also we make a natural gradient descent in the space of probability distributions, which means we learn a variable metric, which means we learn a new problem representation, which means the process is invariant under changes of the coordinate system, given we also change the initial solution. And we update the step size based on non-local information, which means exploiting correlations in the history of steps. And you can still ask questions. This is the complete algorithm.
So,
yes?
so it's going to be heavily dependent on your parameterization of the problem then, because your maximum entropy distribution is not invariant to transformations of the problem.
No, I think the point, well, generally that's always true.
Yeah.
Optimization heavily depends on the parameterization of the problem, but the method actually tries to make it less dependent on the problem. But it's also, you can also learn basically linear transformations of the problem. And still it takes long to learn them. So it's always a good idea to have the best formulation, the best encoding of the problem. But clearly, ill conditioning and in general, it learns a linear transformation, arbitrary linear transformation, and potentially the optimal linear transformation to solve the problem. Does it answer your question? Okay, this is the complete algorithm. One point to notice is, okay, there are some details I didn't present, it still fits on one slide. So we sample the distribution, we update the mean, that's pretty trivial. We update the step size by constructing a path, a search path, and we update the covariance matrix. Actually, we use also a search path for the update of the covariance matrix. Okay, the details are not so important here. One point I want to make is that we have a bunch of parameters in the algorithm. So all the internal algorithms, internal parameters are in green. But actually, they're internal parameters. So they actually don't depend really on the objective function, which is in a way surprising. They mainly depend on the search space dimension. So they sort of depend on the sampling distribution, but not on the objective function, which is an important point. The second point I want to make is the input to the algorithm. So there's sort of one parameter left, which is the number of samples we are using per iteration, and that's indeed a parameter which very much determines the behavior on some objective functions. So if we use a small number of samples, the algorithm converges fast. It's still robust, but it converges fast, and it will often find a local optimum. If the sample size is larger, we will often find more global optima. So really the search characteristic of the algorithm changes by using lambda, and we have its input, the starting solution, and starting variance or standard deviation. Okay. So, okay, I promised to go back to this question of invariance. So here are, I think I don't have so much time left. Yes. Okay, so there are a bunch of design principles in the algorithm. One of them we have actually already seen. It's stationarity or unbiasedness, to choose the factors. To choose, for example, this factor. That's simply, if you want to have the algorithm unbiased, then it's basically determined how to choose it. Okay, we try to put the least number of assumptions possible. We try to exploit all information. It was not so obvious here. Maybe more importantly, maybe it's almost parameterless. As I said, the user don't have to choose of many parameters to actually apply the algorithm. But of course, the problem encoding is a very important thing, which the user should actually take care of to present the problem in the black box in the right way, or in a good way, as good as possible. And there's an invariance property and design principle, which is to retain or introduce invariance properties. And so I already said that the algorithm is independent of the coordinate system, which is an invariant property. So under coordinate system changes, well, if you also change the initial state of the algorithm, the behavior will be exactly identical. The algorithm invariant under, well, okay, you could argue the natural gradient descent is invariant under changes of the parameterization of the probability distribution, at least to a certain extent. And the last point, there were also a few questions about that. It's again about the weights, or why do we use a ranking? It's invariance under monotone transformation of the f-value. So you see here 3 functions. This is a quadratic function. These are 1D functions, but okay, you could think of higher dimensions. And what you see here are monotonous transformation of the functions. So if you would ask the question which one is the most easy, obviously you would say, okay, this one is really easy to optimize. But in our scenario, these functions are exactly equivalent. So they are all equivalently easy or difficult. So if the algorithm can reasonably fast optimize this one, it also can handle these 2. And it's simply, the reason is that we have a fitness function which is composed of g of h, and g is a monotonously increasing function from R to R. and the algorithm behaves identically in any case because the ranking between solutions doesn't change by a monotonous transformation. So that's really a strong property of the algorithm, and that's one reason why we could call it actually function value free algorithm, not only derivative free algorithm. Okay, so okay, I have a bunch of slides about experimental validation. The first one is actually a meta experimental validation slides. So we can basically say that in the domain of evolutionary computation, CMA-ES is state of the art. We have more than 1,000 citations to the two seminal papers, way more than 100 applications which are published. It's implemented in libraries in evolutionary computation, pattern search, machine learning, robotics, chart analysis, water model calibration. I'm sure there are more of them, and we see about 20 or actually almost 30 daily hits on the source code download page, so it's very well recognized. So maybe, okay, I have a bunch of experimental results. Maybe I skip them. If you're interested, I will I'm happy to show them to you. So this is the last slide. Try to give the limitations of the method in terms of practical view. So I forgot to mention, okay, let's go back to here. So what is hidden here is, well, the numerical complexity, or the most difficult part of the algorithm is actually to compute the inverse of C. And here also you have to take a decomposition of C to actually sample these numbers. And this is of cubic complexity, so that's the most numerical complex part of the algorithm. One nice thing is you can use the same decomposition, the eigendecomposition of C for both. The other nice thing is you don't need to do it in each iteration, which means if you do it only after n iteration, the complexity becomes quadratic, and that's what we do in practice. And it basically has no impact on the performance of the algorithm. So you can argue reasonably well that the complexity is quadratic in the dimension, the internal complexity. And so this is the number, it's 10 to the minus 8 times n squared seconds per function evaluation on a 2 gigahertz PC. That means we can do 1 million function evaluations in 100D in about 100 seconds. Okay, that's the number, and one can compute any other from these ones. The question on which problems we should apply this algorithm, well, certainly one point here is if we have a partly separable problem and we can exploit the separability, then you will for sure find algorithms which are better, because this algorithm is independent of the coordinate system, so it doesn't have any clue about the coordinate system. But if you can exploit the coordinate system, there might be real chances that you can be far better than CMA. That's one. Of course, if we know about the problem, or if you have cheap gradients, we probably find better methods. In small dimensions, so much smaller than 10, for example, Nelder-Mead is usually better than CMA. And that's pretty generic, but it seems to be almost always true, which is pretty surprising. Just one feature, of course, to differentiate search algorithms. It's simply the number of function evaluations we do. So if you only do something like 100 times n function evaluations, probably evolutionary algorithm methods are not the method of choice. But if you can do like 1,000 n function evaluations, then CMA might be a really good method to do. So for lower number function evaluations, typically model-based methods are pretty good. Okay, that's it. You can download source code from my page. You will find it on the internet easily. Thanks.
We have time for 2 questions.
I'm wondering if there's a useful limit where you only ever take population size of 2. I mean, of 1 probably wouldn't work because then you can't compare.
Yes.
But of 2 you could always take the better sample, and then you only need to update on 1 sample, so you would presumably be able to do computationally efficient update on the inverse covariance matrix just based on that 1 example. Is that something you've looked at?
Yes, it turns out that's also a really surprising result, that up to about n, you get, okay, so the question is, what do you want? If you want to have a small population size, you probably want fast convergence, right? That's your aim. It turns out that you can, if you look at convergence rates, that they're basically independent of the population size up to population size of n, which is the dimension. So whether you take 2 or 10 and 20D is basically not relevant. Actually, 2 is even suboptimal. So you know if mu is 1, which means if you just select one sample for the update, then you know that the optimal population size is 5. So 1,5 would be optimal in this case. But still, if you take larger population size, you basically don't lose anything in terms of convergence speed up to well, something like the dimensionality. That you can basically compute. Otherwise, you are just more local and more global, depending on what you want. And if sometimes you really want to find the closest nearby optimum. If you want this, then you would indeed use a very small population size.
I see.
With regard to the update, the averages anyway, so the update is low dimensional anyway.
Oh, I see. But then shouldn't it be more efficient than?
So thank you again.